Welcome, everyone. I'm Yonik Seeley, and I'm going to be talking about native code, off-heap data structures, and some other stuff we've been doing in Heliosearch. So this presentation is way too short for 30 minutes, so I'm going to have to really fly through some of these slides. I did want to mention, though, that I started Solr in 2004, and so this year is actually Solr's 10th anniversary. So the Heliosearch Project is sort of what I've dubbed like the next evolution of Solr. It's really just a fork of Apache Solr. We're developing it on GitHub, just trying to do some cool new things. And we started in January this year. And we're following all the Apache IP rules and its Apache license and stuff like that. It's currently a drop-in replacement for Solr at the HTTP API level. And it's really just like under the covers that things have been changed. And we're also trying to maintain it as a superset. So every new release of Heliosearch has the latest release of Solr. So a little bit about garbage collection. This is one of those slides. It's just background. I'm going to like fly right through it. It's just the basics of garbage collection. You trace live objects, copy them all, leave the garbage behind, and that's essentially how it works. Although most garbage collections, or all garbage collectors that I know of, all have this stop the world problem, where you get into a situation where all the application threads stop, application level threads stop, and it makes it essentially look like it's dead. Java is also not the most memory efficient. One problem is you have to set a max heap high enough so that you're never going to run into an out-of-memory error, because that just brings your process down. That's no good. But when you give Java a lot of memory, it tends to use it, and it tends to not be good at giving it back to you. So C, on the other hand, is a little bit different. C has a heap also, but it tends to keep much smaller, because what most modern operating systems and C libraries do is that when you ask for a big chunk of memory, it directly asks the operating system to mmap. And so it gets a big chunk of memory, and the benefit is when you call free, it gives it back to the operating system, where it can then be given out to another process, or the operating system itself can use it to cache the index files and make searching faster. So GC, it lowers throughput because it's spending CPU cycles on copying memory around. That could otherwise be spent, solving your application needs. The stop world pauses, they can be seconds to minutes long. They're proportional to heap size, so the bigger heap sizes you have to run with, the longer the GC pauses. And it gets really hairy if you have big GC pauses and you're running Solr Cloud, it can cause Zookeeper session timeouts. And so it can make what might be just a small problem into a much cascading bigger problem. So GC tuning, just say no. These are all the possible JVM parameters. And what really sucks is to push this problem off onto ops people and developers. And everybody has to solve this problem for their own particular application because of the different usage patterns. It'd be really nice if we could solve it at a lower level once for everybody. And so, ways to reduce garbage collection or just garbage in general is, number one is reusing objects, but that can only get you so far. Number two is moving objects off the heap. So basically some of these big data structures don't use the Java heap at all. And so that's, there are two ways to do that. One is direct byte buffers. They have a number of disadvantages, the main one being you can't call free. So you're still relying on garbage collection to eventually free up your memory. And then option two is something called unsafe, which essentially gives you direct access to memory, including malloc and free. And so that's the option that we've gone with. And so we first implemented off-heap filters, off-heap FieldCache. And so how I tested it was just just did back-of-the-envelope calculations. How many filters would it take to start stressing memory, or should it? And so I just tested an index of 50 million docs with 500 unique filters and just hammered it with a bunch of threads. And this is the result. The graph on the top is straight Apache Solr, and those gray bars, the wide gray bars, are stop the world garbage collection pauses. And so I got a bunch of them on my first try. Now they're only a second long, not too bad, but the heap wasn't that big either. I had to set it to like 4 gig to avoid it running out of memory. Heliosearch, on the other hand, when it had the off-heap filters, on the bottom, you can see that it had, you probably can't read the graphs from that distance, but there were 0 full GC pauses. So we went from like 30 full GC pauses to 0 full GC pauses. And the graph is a lot shorter because it finished faster because it wasn't doing all that GC work. This is just another way of looking at it. The graph at the top is the query latency. So you can see the latencies are pretty much identical. It doesn't really matter too much. It's just really the outliers when that GC hits that causes all the problems. And that's what causes the corresponding drop in throughput. So since it works so well for the filter cache, next we did some off-heap FieldCache. The field cache is used when you have an index field and you uninvert it for the purposes of doing things like sorting, grouping, faceting, things like that, and function queries, the value for function queries. And so we dubbed it like the N cache, and it's for native, and it's an off-heap cache, and it's first-class Solr cache, so you can configure things like warming policies and maximum sizes, and you can see the stats in the admin screen. And so this is what it looks like in the admin screen. And this is just like a blown-up version. It sort of like gives you some example of what some of the stats that you can see, such as like the number of uses, the number of segments. It's a top-level view, but it's still per segment cache, so it's NRT friendly. And of course, size and bytes. So we first implemented support for integer fields, off-heap integer fields. So this test is, again, 50 million document index, 4 request threads, and we just hammered it with random. These were like star.star queries, so very simple queries. And so we tried to just measure the impact on sorting, and so it turned out to be 42% faster sorting, and function queries, a function query of 2 random integer fields, turned out to be 73% faster. And this is really fantastic because we weren't even really trying to speed things up. We were just trying to get it off the heap. So this isn't even under memory pressure or anything. It's just an extra bonus. So next we implemented, after all the numeric types, we implemented string fields. And so this graph is just showing latency. So the Heliosearch is in green, lower is better. And so you can see we got a performance boost there. But of course, the real test is always like throughput. When you're just hammering it with random sorting on random fields in random order, just so hotspot won't over-specialize or anything like that. And we got, in general, a 50% performance improvement there. So let's move on to native code. So the big idea here was, not so unique, but take a CPU hotspot, right? And then try to do some native code in C or C++ to make it faster than what Java might be able to do. The problem is, JNI sucks for dealing with big data structures because you try to pass an array to native code, and the JVM will either copy it or you can try to lock it, but then it's going to lock the garbage collector, pause the garbage collector. There's no real good way to do it, except if your data is already off heap. If your data is already off heap, you're essentially just passing a pointer. Java doesn't even know what you're doing. So first we implemented native single-valued string faceting. Since we already had our string field cache off heap, now we can do facet on it off heap. And so we wrote this code in C++, compiled it with GCC, and it's supported on all the major 64-bit platforms. Another note is static compilation. Another benefit is that it avoids the variances that you get in Hotspot. Hotspot tries to guess how to compile your code best, right? And so, depending on what your workload looks like when you start up, you can get slow runs or fast runs. But when we statically compile stuff, it's compiled now. It's not going to change. And so here's the results we got on our native code faceting. And they were really good. It was like on all the platforms. I tested on these are just my home boxes. That's why the bars are so different based on platform, because they're different CPUs, different architectures. But on every architecture I tested, we got at least double the performance. Then we also optimized the terms query performance. This is terms query. This is a new query that was introduced in Solr 4.10. That's if you're trying to match a large number of terms in the same field, you should use terms query instead of a Boolean query. And so this graph is just showing how both Heliosearch and Solr are faster than a Boolean query. And so, like for example, in the first column, Solr is 1.42 times faster than a Boolean query, and Heliosearch was 2.47 times faster than a Boolean query. That's how you read this. And of course, so we got some good performance improvements, except right in the middle where Solr is faster than Heliosearch for some reason. I haven't figured that one out yet. So while we were running the last test, just like, observed the process size externally, like through top, and just saw how big the processes got. And then we also turned on GC logging to see how much garbage was being produced. And so, as you can see on the far right side, Heliosearch, it had the process size didn't get nearly as big, and the amount of garbage produced was, minuscule compared to, Solr. All right. Now let's talk about the new faceting module. This is the other thing I've been working on recently. So, the Solr's faceting has been getting kind of like the simple facets has been getting kind of old. It's like, it's been around, the code's been around since 2005, I think, and we keep hacking on it and adding on it. So it was really like we took an approach to try to rewrite the faceting module to give it things like first-class JSON support. And with first-class JSON support, we get like easier programmatic construction of like complex facet queries. That's easier for to write a program. Has a more regular structure, and that goes for the response format too. We're trying to provide a more regular structure for parsing facets. So if you pass in change a little parameter, it's not going to completely change the types of structure you get back from the faceting. We also wanted, of course, first-class analytics support. We wanted a cleaner way to hook in distributed search, and really just a better way for integration of various search features in general. So you talk about things like that. We have a lot of different disparate search features, things like joins and grouping, and analytics, statistics, and even things that we haven't thought of yet in the future. We need a good base to sort of meld all those things together in a very powerful way. Of course, one point, though, is that we're not replacing Solr's faceting module in Heliosearch. It really sits alongside it. So if you still want to use Solr's faceting, you can. And you'll get the faster faceting because of the native code optimizations. But if you want to use the Heliosearch, you can. Or you can just mix and match and use both in the same request. So here's just a little bit of an API comparison from an aesthetic point of view. It's just, all it is 2 range queries in a single request. And so, sort of the old styles on the left-hand side, where you just, set a bunch of query parameters. And then the new JSON is on the right-hand side. And obviously, the JSON is better because it's colored. So facets has been traditionally about counts, right? It's like everything's, we're finding document counts, we're sorting by document counts. So what we really wanted to do is extend things beyond that to general statistics. And so now we've added things like, sum, average, min, max of functions in general. And so the arguments here can be like full function queries, basically combining multiple numeric fields. And we also have like unique on, it's currently only on string fields. That'll give you the number of unique values in a different field for each facet bucket. So here is the simplest example I could come up with of a request and a response with the new Facet API. So it's full command, so you can see you even have the curl thing up there, and then you say json.facet, that's the new parameter, and then you give it the JSON. And you see we have a bunch of comments and stuff in there too. That actually works verbatim if you cut and pasted it, because our JSON parser accepts both style comments, and it also accepts things like unquoted simple strings, like you notice X and Y are unquoted, and it'll also accept either single quotes or double quotes. All this is to also make it easy, not just for programmatic construction, but for construction of stuff by hand, or like embedding in strings in another programming language or something. So that's why the different types of quoting. So in this simplest example, we're asking for the average price, and we're asking for it to come back as X. And then we're asking for the number of unique values in the brand field, and label that Y. Now notice we didn't even give faceting like a field facet or a range facet or anything like that. And that is because there is an implicit facet bucket that is produced by the main query and all the filters, basically the documents that match the main query and all the filters. That's where you get your base facet bucket. And so really, when you facet, everything else is a sub-facet. And so you can see our simple response. We get the number of documents in our facet bucket, which is really just like the top level, the number of documents that match the query and the filters. And then we get our X and Y back. So here's an actual terms facet example. And I obviously didn't get a chance to finish coloring that this morning, so it's not quite as good. But so we're asking for the shoes. We're labeling it shoes. It's a terms facet. I use terms instead of field because otherwise you'd have two fields in a row. It's just like an aesthetics thing. I didn't want to say field facet with the field name. So it's a terms facet with the field name shoe style. And that basically creates buckets based on the unique values in the shoe style field. And then we have another facet command in there. It's basically sub-facets saying, give me the average price, name it X, give me the unique brands, name it Y. And so then in our response, on the right-hand side, we have our shoes facet, and it has something called buckets that just list out the buckets that were created. And each bucket has a val, and that's the value in, for shoe style, so hiking shoes in this case, the count, the number of documents that match that bucket, and then the other facets that you asked for, or the other statistics that you asked for, X and Y. So sub-facets are basically, the ability to nest other facets under anything that produces facet buckets. So you can start off with a range facet, and then have a terms facet under that, and then have a query facet under that, and then have another. There's no limit to how much you can nest these facets. In fact, you can have like a number of sub-facets too at any given level. This is basically starting off with our previous example. The only thing we changed was we added to our sub-facets, instead of just X and Y, we asked for a colors facet, which is basically the terms of the color field. And so now when we see our response, we can see that in addition to X and Y, in every bucket, there's a colors facet that has its own buckets. And so we can see that for hiking shoes, 12 of them are brown and 10 of them are black. So this is really just documentation. I'm not going to go over it all. I'll just point out the differences between Heliosearch and Solr in this. It's like the sort. Solr, essentially, you can sort by count, descending, or index, ascending. In Heliosearch, you can sort by count, ascending or descending, and index, ascending or descending, or any of the statistics that are generated for that bucket also. We also have the num buckets parameter. That's sort of different. You can ask for the number of facet buckets that were created. So you may only return the top 10 buckets by any criteria, but you can also get the fact that there were like thousands of buckets. You can get that information back. And then there's also the all buckets bucket. So all buckets equals true, and then you get back this single bucket that represents the union of all the other buckets. So this is a query facet example. It's pretty simple. It basically creates a bucket from the documents that match the query that it's given. And so it defaults to a Lucene query. And so it's essentially like just adding another filter in a way. And so in our example, our second example below, you can see that we have another query, and then we have a whole bunch of sub-facets under that. And so it's really just, like I say, it's really just a way to add another filter and then break things out further by that. And so we have average price, we have another terms facet on the color field, and then here's an example too of a range facet where we just give the field, the start, end, and gap, and it creates range buckets based on that. So range facet, again, this is really just documentation for people who are going to look at this later. This is pretty much just, not pretty much, this is really just taken from Solr. It's, the parameter values and the semantics of those parameter values, there was no need to change those and stuff. That would have just, created more confusion, I think. So we just pretty much used it verbatim. So if you know how to do range faceting in Solr, then with all this hard end and all these different parameters, then you know how to do it in Heliosearch already too. So hopefully you realize, with these, sub-facets and facet functions, you can do some pretty cool business analytics or business intelligence types of applications. So this is just something that I mocked up quick. And so if you look, the top graph is, we're dealing with, in general, we're dealing with revenue instead of document count here. So the top graph is showing revenue over time broken out by genre. And so this company has multiple bookstore chains. And so then the graph below has that revenue broken out over time by the bookstore chain. And then if we go down to the bottom, you can see we have the top genres across all books and all chains with the top genres with the revenue for each. And then under each genre, we have the top authors for that genre, again, sorted by revenue, and then the top books. And then on the left-hand side, we just have more like filters and stuff, how people could click on links to sort of narrow down and change the view. So this is how we'd sort of go about implementing this with the new Facet API. We'd start off with breaking things out by date with a range facet. And so you specify the field, and you specify the start, the end, whatever you want, and then the gap of +1 month. Actually, I think that should read actually +1 month spelled out, not +1M. I don't know. Haas isn't here, is he? I don't remember. I think it's +1 month, though. So that creates our date facet buckets. And then we ask for sub-facets for each bucket. And the first is a terms facet on the genre field. And that will give us, and the terms facet on the genre field. But for every of those buckets, we ask for sum of sales and label it revenue. And that will give us all the data for the graph, the first graph. And then for the second graph, we just add another sub-facet, and it's another terms facet on the chain field. And again, we ask for revenue as sum of sales, and that will give us all the data we need to construct the bottom graph. So, and now for the bottom part of our application, we start off with a genre terms facet. So we're doing another terms facet on the genre field. We're asking for revenue, the sum of sales, and then we have sub-facets terms on the author field, and we're asking for revenue, the sum of sales, and we're sorting by revenue descending to get just the top ones and limiting it to 3. Now you'll notice that this, defining revenue to be the sum of sales and sorting by revenue descending, that's like repeated over and over here. That is something that I hope to fix in the next release, probably through some sort of default mechanism, so you don't have to like specify this in multiple places in the event that you do have a lot of sub-facets that are just doing the same thing, but just breaking down by different criteria. And then, for books, the same thing. It's like a terms facet on the title field, ask for revenue, sort by descending. And then the filters, essentially the same thing for the state filter. We're retrieving 2 numbers here. So we're asking for revenue, of course, but we're also asking for the number of stores in each state. And so, we broke out first by state by doing a terms facet on it. But then we're asking for, we're calculating num stores by using the unique function on the store field. And so that will just figure out the number, even though there may be multiple entries for each store, it'll just collapse it down and find the number of unique stores for each state. And the same thing for the chain and store. Okay. Some miscellaneous features that we've also developed recently. One is parameter substitution. So this is very much just like shell expansion. It's $, curly brace, and then the parameter name. The cool thing about this, though, and what makes it a little bit different, is that it is done at a very low level across the entire request. And so what this means is you don't have to follow any syntax rules. It's not like it can only be used in certain places. It can be used anywhere because it's been done at such a low level. So for example, you could templatize some JSON facet commands or something like that. So it allows default values, so you can do just :default value. And they can also be nested. So you can have one parameter substitution that itself has multiple parameter substitutions and so on. And lastly, we've put in some new query parser features that are just little nice to haves. The first one is basically a filter keyword. And so what this does, it's essentially like an FQ. It goes to the filter cache, retrieves the set of documents that match things that are surrounded by the filter clause. And if it's not there, it generates it and caches it. So this is just like an FQ, but you can put it anywhere inside a Lucene query. So you can just mix and match. You can do ORs of filters finally, things like that. We also developed a syntax for constant score query. If you recall, a normal boost query is clause, caret, and then the boost value, and that's a multiplicative boost. So the syntax we came up with is just that caret, but then an equals, and then on what's on the right-hand side is just gets assigned. That's actually the score that will be produced instead of boosting. And then lastly, we have comments and queries, and that just lets us they're C-style comments, but they can also be nested. And so that's nice if you have a very big query, being able to annotate parts of it, but not have it actually change anything. Oh, and one last announcement I wanted to make. We are currently working on integrating SirenDB, which is basically allows you to index a JSON field in your document. And then you can do really cool structured search on that JSON. And so if you want to know more about that, Renaud has a talk about it. I think it's in the diplomat room right after this. So I encourage you to, if you want to know more about that, go check out that talk. Thank you.